Good lunchtime. Welcome to Ask the Expert with Dr. Rob Moorehead and Dr. Will Pulfrey. We'll be talking all things imaging characterization with Rob and all things advanced metals processing with Will. So I'm going to hand over to them, let them introduce themselves, and we'll be taking your questions if you want to pop those in the Q&A tab, and we will be addressing those throughout the session.
Hi, yes, my name is Dr. Rob Moorehead, and I'm the Technical Manager for Experimental and Characterization at the School of Chemical, Materials and Biological Engineering here at the University of Sheffield.
I am the Technical Manager for Advanced Metal Processing and Thermomechanical Processing in the Royce Institute at the University of Sheffield.
So do you want to take it away and tell us what the advanced metal processing can achieve here and what we want to do?
Because I specifically manage the thermomechanical processing stuff. So that's from hot rolling, conform, thermomechanical compression, including HIP or hot isostatic pressing. So we cover that kind of area. But within advanced metal processing, we go from alloy manufacturing. We've got additive manufacturing, which George Madison did a couple of months ago now. But I guess, because we're trying to think about how we can kind of link these together, can't we, in terms of what overlap we have. And I thought what would be probably most appropriate would be, so at the start of the journey, we start with alloy creation. So Eunice will cast some novel composition, and then from there, well, how do we know if it's any good? What would we do? So some of the things that then Rob would tend to do or has the capability of would be.
Yeah, so after the casting, I suppose one of the big questions that you have is the elemental composition that you've created. Have you done it correctly? What is the purity where you want it to be? What is the crystal structure like? And that's some of the questions that we can help answer. So we have X-ray fluorescence spectroscopy, which looks at the elemental composition. We can also support that with ITP to really dial in exactly what the composition is. And we hope to be able to offer glow discharge, OES, soon as well to further confirm that elemental composition. And then you've got the crystal structure, which I guess is really, really important to the types of things that these are going to be used for in the future. So I look after the X-ray diffractometry suite here. We have a number of instruments that can collect diffraction patterns and determine the crystal structure of the materials, but also we can do that type of thing at temperature as well. So we can take the material from room temperature up to about 900, 1000 degrees C and collect diffraction patterns all the way up to see if there's any phase changes during that time. And we can also hold there for a long time, so we can do aging of that material.
Yeah,
it's quite exciting.
And I guess so once we kind of got confirmation in terms of, so the material's being processed, we've just cast this novel composition of a metal, and then from there we're happy with the composition through the various things that Rob's just kind of mentioned there, and then we need to process it. So we need to take it from this as cast structure, which we're then going to typically, let's use the rolling mill as an example, we're going to manipulate this into a longer piece so we can make more use of it. But as part of manipulating it into a different shape, the process in doing that, we can change the mechanical properties so we can increase the strength, the toughness, the hardness, the ductility. So through the process of manipulating it to a different geometry for subsequent or post or downstream processing, we can manipulate the mechanical properties. And I guess one of the things that I found quite interesting actually when I first joined was this is meant to be advanced metal processing. Yet we've got a rolling mill. Like rolling's been around since the 1800s. Like everybody kind of knows what rolling is because it's so old. But I think it's something like 90% of all metals that are processed go through some version of rolling. So if you create a novel alloy, which we do here frequently, we'll then get this alloy, and the amount of times that it fails on the rolling mill is kind of staggering. So it's kind of like, well, that's kind of the first test. So we've made it. The structure looks fantastic. We've got, it's fully, it's in solid solution, whatever. But if it can't be processed, then what good is it to people? So from the rolling, like I said, we would then manipulate it into a different shape, size, determined by whatever mechanical properties we want, then maybe subsequent heat treatment. But then from there again, we can stop. Right, so we've cast, we've analysed it, we're happy with the element, we've then processed it, we'll stop, and then back over to Rob.
Yeah, so after you've done that thermomechanical processing, you want to think about what that's done to the grain structure, and that's really important to really understand those improvements in ductility and the hardness that you were talking about. So we can do that here. We have EBSD on our electron microscope, so we can do full EBSD and look at the grain orientation and the grain sizes through that. And also we've got we can do texture measurements on our X-ray diffractometers, so we can look at the texture in more of a bulk way rather than the EBSD way. So those types of characterization techniques are really useful. But also we have techniques that can help us if the material fails. If the material's not ductile enough or is not can't be thermally processed, we can look at those thermal processing characteristics. We have thermal gravimetric analysis, differential thermal analysis. They can tell us about phase changes and melting points and softening regions. And we can do all that here with our characterization equipment, and that can really help inform the research that you're doing to answer the questions rather than just guess at another composition or try another heat treatment or try something else.
Which is incredibly valuable because we get that feedback straight back into the rolling or even alloy manufacturing, and we can then tweak those things to optimize it further downstream. And this is why we have such a huge collaboration with industry, because if you imagine, they've got the rolling mills, they've got the casting equipment, and quite often they've actually got some of the characterization equipment, but not as advanced as the stuff that we have, more generic stuff. But if they were to shut down the production cycle of whatever they're processing, just to kind of we've got this new novel alloy that we're hoping to use in the future, it's going to cost them thousands and thousands of pounds. The downtime of actually stopping the production, and so being able to have the lab scale testing. We can collect all this information and then have a best guess before we then upscale it. So from an industrial perspective, we can kind of optimize it as far as we can before then they do their first trials, which they've kind of already dialed in. So by being able to get all this characterization as well as the processing parameters nailed down, it's humongously valuable.
Being able to operate in that small to medium scale and not having to have any downtime of instruments for manufacturers is invaluable, I imagine. And that high throughput that we can get through, because we can characterize and re-perform the experiments again within days. It's invaluable because we're all based in one building.
We're essentially just rapid prototyping, aren't we? From the base material, so units will start with all the different base ingredients to melting, to processing, to characterizing, can be done within a matter of days. And then, this is slightly off. Right, well, the next iteration. So you could have multiple novel alloys fully processed and characterized within a week, which is something that I think we take for granted. Because when you visit various other facilities, you think, wow, maybe we have got a lot of cool kit here. So it's that's quite
special to be a part of this.
Yeah, it's awesome. So I guess we've kind of covered on rolling a little bit in terms of what we do. One of the things that I've been working on at the moment is the kind of digitalization of stuff. So putting sensors on it, acquiring that data, having that data synchronized with the processing. So again, we've got a better understanding of what we're doing and why we're doing. And if something goes wrong during processing or experimental, we can then compare that. Well, why did that happen? This was the same material or whatever. So that's been quite exciting to work with.
And this is something that's not really readily available in any manufacturing site. They don't have the level of detail that you can collect on the rolling mill. You've got sensors for strain, for temperature in multiple locations.
So it's I think one of the things, it wouldn't necessarily be appropriate for upscaling into an actual production facility, but that's because that's not what we are. But we can put thermocouples within the sample so we can get a thorough understanding of the temperature while processing simultaneously by monitoring the temperature on outside of it, so we can get a really good understanding of the actual temperature of the material as it's getting processed. As well as obviously capturing all the other, the force, the strain, torque, speed, you name it. But that's really valuable again, because one of the situations we have been working on is like nuclear grade steels. And as part of that, the anticipation is that mass steel production of this will take over at some point. So what we're having now is we're having industry come towards us to start processing this on a lab scale, to capture this information now, so that when they do go into that next stage, they've got a really good well, we know that if we have these idealistic conditions, we can achieve this. How does that translate into industry? Who knows? You need to, it might be really cold in the warehouse, or how big is the ingot? How much is the heat loss? But I think that's one of the things that I really find quite fascinating, is that, You can have the theoretical approach where you can do a lot of reading and modeling and simulating stuff, which we also do, but nothing beats actually just doing it and trying it. And we get a bit of a snapshot with the lab scale stuff,
Yeah.
but then seeing that transition into industry is really exciting.
Yeah.
Yeah, I love
And
that
having that
feedback.
depth of information that you're getting from all the sensors on the instruments allows you to give a deeper understanding to those people when you're
Oh
handing it
yeah,
over. If you're saying, well, we're getting this problem, so we've seen that problem when we did this and we
yeah,
changed these parameters, we saw this temperature here.
yeah.
That's when we really got the results that we wanted. So you can
Well,
answer
we
those
had,
questions.
in fact, we had an application the other day where we were processing a particular steel grade,
Mhm.
and what we found was about, I don't know, 7 passes in that the material failed,
Yeah.
which was bizarre in itself. But with looking at the data, actually, when we looked at the force applied, that was straight away was alarm bells because it was erratic, irregular,
Okay.
but like relatively low force throughout. Whereas if we didn't have that information, you'd be like, oh, it failed on the 7th pass. Well, actually, it
Yeah.
failed from the offset. It's just that visually you could see it failing on the 7th pass.
I see. Yeah. Yeah.
So that, the data and sensors pick things up that we can't, especially in real time. Being able to reflect on that and associate that is it's really important and helpful. Um, so yeah, that's kind of
Yeah.
rolling in a nutshell and kind of how it links in with alloy manufacturing, which I think Eunice is going to be doing at some point. So I'll not steal a show for him. Plus, I don't know what I'm talking about with that. So then we process things. Rob can characterize some of those aspects as well.
Yeah.
I guess one of the other things that's probably worth mentioning as well is that we've got powder manufacturing, and we do a lot with powder in a variety of different ways in terms of consolidating that.
Yeah.
But the start of that journey is actually creating the powder.
Mhm.
So again, units can cast, and then we atomize this. So we just basically melt it and shoot high pressure argon and at it, and it just obliterates it. So you get powdered metals.
Yeah.
But from there, uh, for our process specifically, the powders, because it's getting hit with high pressure argon and it obliterates it in a variety of different ways, you'll get
Yeah.
different powder particle sizes and even splashes of stuff. So we
Yeah.
get this massive powder range, which I think George will have talked about last time in terms of, well, they need very specific types of powder,
Mhm.
shapes
Yeah.
and sizes. So once we've created this powder, we then go, Rob, is this any good?
Yeah. Perfect. So traditionally you would take that and you just pass it through a sieve and just start sieving it out into the different grades, but you don't really understand the distribution and how the settings of the atomization can affect that distribution. Here we have particle size analysis instruments that can measure that distribution, so then you can optimize your production to aim at a certain grade. So this is the particle size that I'm really interested in. I can determine that by these settings, and I've tested it with our particle size analysis. We have a master sizer here, and it also has the built-in camera functionality, so we can look at the particle morphology, which equally can
Okay,
have
yeah.
some really big impacts on the way
Oh,
that the
yeah.
structures are made, and how good they are at the sintering in the 3D printers
Yeah.
that we've got here. So I'm sure George went into that quite a lot when he
Yeah.
was doing it, but then, like you were saying, we can process that powder again. So we have a process here that you're in charge of. It's FAST, it's called, right? Field assisted sintering.
Well, yeah, it's certainly within the AMP team, but we've
Yeah,
got other people. Yeah, but that's can be used for powder consolidation for
yeah,
sure, but it's important to know what you're putting in before you start the
exactly,
consolidation side. So
exactly.
that's why, we need that feedback from the powder creation. What are we putting in? What works better? Are they
Yeah,
bigger particle sizes? Are they smaller
yeah.
particle sizes?
And
Irregular
usually with that, you
shapes?
want a wide distribution of particle sizes, but
Yeah,
in certain proportions,
yeah, yeah,
because you want to have a fully densified object to the end of it.
yeah.
And that's one of the questions that we can help answer here as well, is that we've got the ability to measure the pore size and the pore size distribution for some of the equipment that we've got. We've got porosimeters, both helium and mercury porosimeters here that can evaluate that for you. And we have the Archimedes principle, obviously, to look at those internal pores.
Yeah,
Uh,
which is incredibly helpful because, I
yeah,
mean, in terms of, when we are processing things, we always want, unless you don't, but we always want to aim for full consolidation. So having techniques where we can understand if has it worked, has it
yeah,
not, and
yeah.
and because my understanding was the only thing you could do is the Archimedes water test, but I don't think
Mhm.
that is the case. You can use different techniques.
Yeah, these porosimetry techniques
Yeah,
look at not only the pore sizes, but the pore geometries and
yeah,
whether they're interconnected or not. And it might not necessarily be in the field of advanced metal processing, but for lots of biomaterials, the pore size and the pore size distribution is like really, really important, because you want to know how the cells of the body are going to get into those performant materials, and how the cells can attach, and it's really, really related to the pore size and interconnectedness of those pores.
I think that was really interesting actually you say that, because we would be really interested to understand the pore sizes and distribution throughout something as we're processing it, because if we're processing powder or swarf in a particular way, that wherever that pressure is applied, we're seeing visually that we're getting a range of different consolidation. So actually, if you could actually quantify, well, from this point, loads of pores, this point, less pores, and you can, are they connected, are they not? And we can then attribute that to how we're processing that, and we can maybe try and change the way that we're trying to process to eliminate that. So again, it's that having that continual feedback all under one roof, which makes things so easy and quick. But it's ultimately helpful because we can get to that solution much quicker.
I think that's the big advantage that we have here, is that we've got that integration, and we also have all the sample preparation equipment that you need for that. So taking those large discs, cutting them down for sample sizes, so you can have different parts of the sample in the machine at different times. So you can really understand it.
Because then that, I guess, does that tie into the SEM and looking at the microstructure post-processing from, say, some thermomechanical processing?
So any type of processing that we do here for them, from the ceramics, from compression, from the hip, you want to know what the surface is going to look like in most cases, because the surface is what interacts with the outside world. And we have a wide suite of SEM capabilities here to look at that on the finest detail to the zoomed out macro scale. Other things that we have here that you're thinking about surfaces and the structure and how solid things are, we have atomic force microscopy, which can be really useful for looking at local topographies and for understanding mechanics at a very small scale. So for softer materials, it's really, really useful. So we have a suite of atomic force microscopes here for just that type of thing.
So you're saying atomic force, like what does that, are we talking atom point? Well, obviously not atom point, but is it?
Well, yeah, we are. We're talking at the smaller fine scales. The equipment can be used for. So atomic force microscope is basically taking the principles of like a record player. So we have a needle that's going in a groove, and it's measuring the height and changing the amplitude of the sound. But instead, what we do is we use feedback to vibrate the needle, and then as it touches the surface, the vibration amplitude will change. And then for some clever electronics, we can change the height of the scanner to measure then where the surface is. And we can feel the surface. And the tip of this needle is, it can be as small as you like, but it's generally around 20 atoms wide. Something like that. It's incredible. And then we can measure these incredibly tiny geometries. So we've had great success in measuring the big one that we do here is measuring the size of DNA molecules, things like that. And not only the height of it, which is about 3 nanometers, but measuring the grooves. So we all know that it's a double helical structure, so it's like a double helix, but those helix have different widths. So it's almost like one is close together and the other one is wider apart, and we can measure those major and minor grooves in DNA molecules and look at the conformations that they form. So I don't know if you know this. It's a bit outside the wheelhouse of AMP. But in every cell of your body, you have 2 meters of DNA, 2 meters in length of DNA, and it's 3 nanometers wide. And I don't know if you've ever had like reels of cotton that have unreeled in your hands, how knotted it gets and how complicated that challenge is to unknot it and to be able to use it. So the cells in your body are trying to constantly read what this DNA is like. I'm no expert, but when it's all tangled up like that, it's really, really difficult. So they have different protein molecules that can kind of untangle this, and knowing the way that the body deals with this type of thing really gets to the heart of like how your body functions and how diseases occur when there is malfunctions in this type of process.
So how do you isolate like a single strand of DNA to then like pin it down? Like, you stay there, we're going to measure you now. Like, is that?
So there's a couple of ways to do it, and the most common way, and the way that we do here, is we take small sections and make little loops out of it. So if it's untangled at both ends, it's really complicated and really long. But we can take sections of the code and use bacteria to make them into a loop, and they do that up in the med school. And we deal with a lot of research from the medical school here and also across the UK.
Sorry,
particularly with the Crick Institute, we've worked with them widely to look at the materials that they've created, the DNA loops and interactions with the proteins. So all this is related to work with Alice Pine, and I'm sure has been on these tests, and she's the head of imaging and characterization for Royce currently. and it's really fascinating to see these materials under the microscope in this such high detail, and how they interact with proteins in their natural environment, because you can do this thing wet, so it's not, you don't have to dry things out like you do for SEM. So you can do this live, if you will.
And I've now got an image of bacteria like herding around some DNA, chewing it until it gets to certain. So you said you use bacteria to make it form a ring.
Yeah, it's really complicated. And definitely beyond my skill. Skill level. So
plus we've only got half an hour.
Yeah.
Well,
we'd have to bring Alice back in, and she could explain this much better than me, or Matt Newton, who's a researcher here, who's just got the laser tweezers. So you put your molecule and you hold both ends of it with lasers, and then you pull it apart, and you can see how it tangles up and how it untangles itself.
That's
you pull
wild.
It apart. That's we have a thing called the C-trap upstairs, which is again another piece of Royce imaging and characterization equipment that can do this thing. And then you can also put proteins on the molecules as well. So when you pull them apart, what's happening to the protein? It's a really fascinating technique that I'm not fully understanding of, but it's really exciting to be able to have it here and to be able to offer it to the researchers in the UK.
So I mean, from characterization, then you can literally go from millimeters right down to atoms.
Yeah.
Wide stuff.
Yeah.
What does it get after nanometers?
The angstroms.
Angstroms.
That's what we're measuring. So I whenever my friends and family ask me, "What do you do for a living?" I say, "I measure the distance between atoms," and that's the standard that we work with. Yeah. What do you do? Yeah. I measure very small things. A very small ruler. It's really exciting. That's the best thing about working here at the School of Chemical Materials and Biological Engineering, is that we cover this wide gamut. For characterization, you have to be involved in everything. We are involved with the cement groups here, looking at how the cements change over time with the XRD. We're involved with the nuclear group here, looking at the radioactive waste materials, waste-containing glasses, how they degrade over time, looking at the surfaces, looking at the bulk material. It's really exciting. We work with the biologists, looking at these DNA molecules, but also looking at bacteria, looking at cells, cell stiffnesses, and stuff like that. It's fascinating. That's the best part of this job, and I think I mentioned this when we did the Meet the Experts videos previously, is that working with such a wide gamut of people is really what makes this job really exciting. And like what you say is, and you don't work just with people within the university.
No.
And within your school, you work across universities. You get to work across different companies and small enterprises that are just starting out, to big enterprises that are doing fantastic things and generating billions in income. It's the best job in the world.
Yeah, it is damn good. And I think you kind of hit it there, especially because I quite like working with the SMEs, because not only do we have the access schemes that makes them be able to utilize this equipment subsidized, aka free, but then they get the whole suite of the equipment that we have and the experience that we have with all the technical staff involved with that, and also academic staff. But then we can actually see what we're doing and how they can then use that going forward. Which I don't think you necessarily always get with bigger companies, because it might just get lost. You never hear anything about it ever again. And in 5 years' time, it's like, oh, I think we did something on that. But with the SMEs, you get a lot more feedback, interaction. You get to see their facilities and what they're doing and working towards. And I think that's really good. I think that's one of the best parts, working with industry and smaller scale industry at that.
Yeah, it's a key driver for the UK economy, and part of the UK business strategy is all about materials. And so I think it really ties in what we offer here at Royce.
Yeah, absolutely. Yeah. So I think we've probably covered everything that we'd thought of, have we? Maybe.
Broadly, I think we've waffled.
We have definitely waffled. We're good at that. We are good at that.
Yeah.
We had an hour-long meeting to kind of prep for this, and ended up spending 5 minutes prepping for it and 55 minutes talking. So it's, but
yeah. So if anybody has any questions online out in TV land, we'll be happy to answer any questions that you have.
I think you've probably answered everyone's questions in all of that. It's absolutely fascinating. Is there anything else that you haven't covered yet that you would like to before we wrap up?
Shoehorning. Have you writing any books or anything that you want to promote or sell?
Yeah. We are open for business from institutions across the UK. and industries, like you were saying, through the SME access schemes. I think they're the real valuable parts of what Royce is delivering.
Yeah.
And there's not just our institution here in Sheffield, there's institutions across the UK offering everything. If you go to royce.ac.uk, you can see the breadth of research that we're into and the breadth of access that you will have available to you. If you're a researcher in the UK, you should definitely be reaching out to these things, because we can really help out and really accelerate your research, really put you on a steep trajectory for researchers and students alike.
Do you think you could summarize everything that you do in kind of one snippet? Like, we can measure things from millimeter to angstroms.
Yeah. So I'd say more broader than that. We're here to help you answer the questions that you have, to help you solve the problems that you might be having with manufacturing, from the very initial conversations around, can we make this work, and why is this not working? So that more broadly, we need to improve our yields, things like that. We can really, we're here to support UK industry and UK research to answer those questions.
Yeah.
And we're funded by UKRI to do that. So reaching out is definitely the thing to do.
Yeah.
Does that make sense?
Yeah, absolutely.
How about yourself?
Well, personally, it's just heat things up, squash it. So that's nice and easy to kind of summarize. But I think collectively, as the AMP team, is we can create any kind of novel composition of a metal that you want to make, process it in a variety of different ways, and get the feedback to understand what we've done, why we've done, and how it affects the end product, and does that fit into what they need. So I guess it's kind of echoing what you said there, is that we can hopefully find a solution to a problem they've got with all the technical staff capabilities that we've got in a pretty damn quick time. So it's, but yeah.
Well, thanks, Will. It's been a pleasure
Thank you, Rob.
today.
He's actually in a different room. He's not sat opposite me. So I've got a little silhouette and a portrait on a wall looking at him. But yeah, it's nice, short and sweet. Got 4 minutes, Ray. You've got 4 minutes to fill now.
If you've got any further questions, the conversation does not need to stop here. You can send those questions over to us, or you can find probably answers through our websites. So as Rob's already mentioned, the Henry Royce Institute website is Royce, that's royce.ac.uk. And then you've also got the University of Sheffield's website as well. And you can find us at sheffield.ac.uk/Royce-Institute. Or get in touch via email. You can get us on royce@sheffield.ac.uk. And we'll be able to pick up any of those conversations with you from there. So thanks very much for joining us. We hope you will join our next webinar. The date is yet to be announced, but do stay tuned to us on LinkedIn or through our website, and we will give you more information when we have a date set. Thank you very much.
Thanks, Ray.
Cheers, guys.